Thank you very much. I'm Peter Clapham. I'm with the Wellcome Trust Sanger Institute. We're based in the other Cambridge, back in England. We're about 10 miles south of Cambridge, where we've been described by our director as a scientific hippie commune. I'm not sure he'd approve of my saying that. So the Wellcome Trust has been running for a while now. Originally, it was put together as a genomics research institute, and it had a single targeted objective, and it was to take part in the Human Genome Project. And the idea was to come up with a first draft of what the human genome actually looked like. Now, this is a huge undertaking. It took 10 years. It was an international collaboration. WashU, Broad, a huge number of significant partners were involved in this. And eventually, the first draft was released, big Nature papers, fantastic. And now here we are, 10 years plus on from that time. We no longer have the draft of one human genome. We actually have tens of thousands, hundreds of thousands, possibly worldwide, millions of genomes available for research. This is a huge amount of data. It's also a huge opportunity. So today, Sanger's research is now split up into a number of core areas. So we have areas involved in infection genomics, in malaria, cellular genetics, human genetics, and cellular aging and somatic mutations. And they're supported by a number of local Sanger core groups, one of which is the IT team. This is a big difference for us. It changes our demographic, it changes the challenges we're seeing, and it changes the type of research that can now be performed. If you've got the draft of one human genome, well, you can look through it and think, well, that's nice, it's ATCG. What does it mean? When you've got two people, you can compare and contrast. When you've got hundreds of thousands with different conditions, you can start to see mutational signatures. Condition A looks the same as condition A in another patient, but there may be subtle differences that have a significant impact on human health and how you might treat that patient. This is becoming increasingly important as we move towards this gene-targeted therapy. So for the past 20 years, we've taken advantage of HPC, traditional HPC. I feel a bit of a fraud because really in genomics world, it's really HTC. We're doing a lot of high throughput computing. It really is a data warehouse problem from day one. The good news is we've partnered with a number of good people over the years. DDN has provided us excellent support in our storage. It's one of the reasons why we're here today. But the traditional clusters have provided us with great scale-out compute, great opportunity for analyzing data at scale, a really good, reliable platform that's solid, it's resilient. And it gives you the best tie-in for your library structures, for your tools that you're providing your customers. But it's not a panacea. We find that something's become constraining. You're tied to a specific library. Your customers are tied to that specific glibc. They're receiving third-party binders from companies that suddenly your cluster, you can't support it unless you upgrade the whole cluster, at which point your other customers are really upset that you've broken their world. So we needed a way of making things more flexible, more adaptable, more amenable to research, particularly when new disruptive technologies come through. So we've recently moved towards a hybrid model. Traditional HPC continues. There's no change there. But we now have a private cloud environment, which we're referring to as a flexible compute environment, because of the flexibility it provides our customers. They can put whatever operating system they like on there, all the things you'd expect from a cloud environment. But it allows them to run Docker, it allows them to have access to root. For a developer, this is a fantastic opportunity. But there's a catch. If you spent 20 plus years in an environment where high-performance file systems are POSIX, all the tools for 20 plus years are written for a POSIX file system. People expect a POSIX file system. Clouds traditionally don't have a high-performance POSIX file system. They have object stores. They have S3-like interfaces. This is a bit of a jump. Actually, this is a massive jump. It is not trivial for somebody who may no longer be a coder. With this increased specialization with research, we're seeing a move away from the original bioinformaticians who were very strong coders, very strong IT basis. We're seeing people now really specific on their R skills, on their SAS skills, and similar. They're no longer the people who are in a position to make this migration necessarily. So we need to provide tools to help people migrate from HPC into more of a cloud environment. So there's less of a jump, less of an impact, and do what we're really trying to do, which is enable science to take place at scale, rapidly, and in a way that's relevant. So how do we attack this problem? How do we provide a POSIX file system that's performance into an environment that doesn't traditionally have this sort of thing? How do we introduce this? And we need to be able to introduce it in such a way that we get the multi-tenant support. Because as we move to research that is designed and geared towards health benefits, there's going to be increasing amounts of personal information in there. So tenant group A really must not be able to see the data from tenant group B. This is not a good fit for most file systems. NFS, which we all know and love, it's nice and easy to set up for a cluster. Traditionally, the ACLs are all on the client side. There are ways around that. There are easy mistakes to make, particularly in an environment where somebody might have root. The same thing with Lustre. Traditionally, Lustre, you would have more of a challenge preventing somebody getting root access in an environment and then doing something with it as somebody else, or making a mistake, which is more likely, and deleting something they shouldn't. As we say, our customers, they don't want to know how the watch was made, they just want to know what the time is. They don't want to know about all the clever stuff in the infrastructure, so we've got to make that go away for them. So it's not good enough just to be clever to find a solution, we've got to make it simple for them to use. So where do we start? Well, we started with what we knew. It's the easiest place to begin. We know about NFS. We didn't really believe the solutions we had available to us were performant enough, wouldn't really do the job. But we had a large infrastructure based around Lustre. And over the years, we've bought a lot of DDN hardware for our Lustre systems. In fact, to be very performant, very effective, very reliable. So we thought this is a great place to start. Maybe if we start with a Lustre system, maybe we can do something with this. Maybe we can do something to adapt it from its traditional export of this file system, standard ACLs, and provide it to customers. Maybe there's a way we can add tenant support to it. So we took an old Lustre system that we had hanging around because we just upgraded it, and we gaffer taped it into our existing network infrastructure. The reason why this was up is because, frankly, we had a lot of bandwidth. You'd expect that in a bioinformatics environment. So it shouldn't get in the way of our testing. At the time we were looking at this, we were going through the README files and the release details for Lustre 2.9. And a few things that really caught our eye. The first one is the ability to fully squash a tenant's UID, GID. And we can restrict that tenant's access to a particular mount point. So if we can actually achieve that, then we should be able to say when somebody mounts the file system for a given tenant group membership, they can only see their mount point, no matter what their permissions are, and then only see their access controls according to what we've restricted them to. So effectively, we should be able to create a jail. So we thought, maybe we can do this and come up with a model for it. So we started off with a traditional OpenStack environment. We thought, okay, you have your public network, you have your router out to the public network, you've got your tenant network area, its own separate administrative domain. Maybe if we put in place a provider network, set that up on its own VLAN, in our case VXLAN, add a Lustre router, and then have our standard Lustre setup, link through from our tenant groups, from their client machines, and the restrictions we place on the server, and the restrictions we can place on the network through OpenStack, and the restrictions we place on the Lustre router, maybe that together would be good enough. Maybe that would do the job without having to resort to huge amounts of SE Linux and Kerberos authentication. So we started and we thought, well, actually, this looks viable. We found this command that we'd never used before. We'd never used the LCTL node map command before. Do we have many people who use Lustre in the audience? Has anyone used the node map command? One. Oh, 1.5. Okay, fine. So basically, this was kind of arcane to us. We hadn't tried this before. We thought, well, let's give it a go. How hard can it be? So we started at the beginning. We created a mapping for a new tenant group using this command. We then took the defaults. For example, root squash is normally turned off. So we turned on root squash. Let's stop root doing anything nasty. We then did the same thing for the standard admin accounts. And then we mapped and squashed the tenants to a specific tenant UID. So now jailed in their own area. That's the idea. The last one there is really for convenience. It means that when people log in, all the files look like they belong to that particular user because they can only see their own files. It's a convenience. The configuration of the server side, again, pretty straightforward. As you'd expect, you need to create a mount point for someone to use. They need their stuff to live somewhere. So we create a directory, we tune it accordingly. And then we set the subroot tree for them to use. So when they log in and they access the Lustre file system, that'll be the top level. They can't see the rest. We've hidden the rest away from them. We then wanted to actually constrain it so only queries from that specific network component could gain access to the router that we're using for the LNet route, and subsequently the actual Lustre system itself. Turns out that was actually pretty simple as well. We could map that again using NodeMap, and we could then statically assign that with a route to the LNet router itself and do the same on the client. That gives you the one-to-one relationship between the two. Great, so we set the server up. Fantastic, that's great. In theory, it should work. All we've got to now be able to connect to it, really. So on the OpenStack side, we want to be able to create a provider network, this back-end network that can see the Lustre system that we've just set up. Great, okay, fine. OpenStack will allow you to do that. But we want to be able to do it in such a way it's restricted so that people who have not been given access to it couldn't automatically mount it themselves, couldn't create that network for themselves. People couldn't spoof the system. So that's fairly simple to do. Again, standard OpenStack commands. By creating the first network for the provider network, we can then assign the routes, we can assign the DHCP servers, and we can tie it all down to the same UID. We can then assign an OpenStack role for this. That means we can tie it down to only those people with that role can then access that network. We found a couple of foibles. Things didn't work quite as we expected to begin with. It turns out there's a default rule in the Newton layer. That's the part that actually deals with all of the networking underneath OpenStack. For those who've used OpenStack, it's pretty familiar. But this is what caught us out. By setting this, we can then control which user-tenant pairing can actually do things. So we set that. The problem went away. The right people could do things again. By increasing the mapping, you can now really tie it down. Nobody else can now touch this unless they are in that role, they are in that group. And these are the only two external configurations we had to make. So that leaves the last part. I've got the server sorted, I've got my clients sorted, I've got a network. I now need a router, LNet router, between the two to link the thing up. We found a couple of bits of hardware again lying around that we could repurpose. Using the OpenStack environment, we could set up some client virtual machines. They only need to be big enough to run the benchmark from. It's basically a I/O benchmark, so it's not anything compute heavy, so it's nice and simple. And we used a Lustre client that matched the same as our Lustre server. We found pretty quickly, actually, it works. It actually worked. That was a big surprise. We expected there to be a lot of to and fro, a lot more work, but it actually just worked out of the box. But when we first looked at it, the physical server looks good. That's fine, fantastic. But when we looked at some of the virtual servers, we found that's just starting to go pretty slow. We had a bit of to and fro with one of our vendors, Mellanox, and it turned out there was a significant issue with one of the kernels, one of the kernel drivers. Updating that, and we were suddenly able to bring the performance up to something that's actually in the right ballpark. For a single-threaded performance, it actually worked really well. Same thing for writes. As soon as we made the kernel update, everything fired into life. Fantastic, I can live with that. But for those who've used Lustre, you'll be very much aware that as you increase the number of clients, the number of threads you throw at it, the more the aggregate performance becomes. You take advantage of more of those disks, more of those storage targets. In this case, throwing 80-odd clients at the system, we were able to hit 3 gigs a second. That's bang on. That's what we're after. That's the sort of target market we had to begin with, particularly with hardware that was 6 years old. That went pretty well. That now means it's actually viable for us to use for our customers. As we added more VMs to it, we were able to increase the performance again, not a problem. And we were able to get the aggregate both from the bare metal NLAT routers and the configuration files that we had. We didn't have to do anything else special to it. Okay, so if we can have a single LNet router, and we put everything through it from all the different networks, that works, but it's a single point of failure. It's quite a large failure domain, and in theory, maybe somebody from another side could sniff something if they ever got access to that LNet router. So could we create virtualized LNet routers for each tenant group? No additional cost or any VMs, how hard can it be? Turns out, if you actually follow that, it worked rather well. We brought up a couple of LNet routers, nice and simple, small VMs, nothing special to them, it's only I/O. And we found that actually, adding this didn't cause a problem at all. We did find there was an issue on port security for our own personal environment, and we needed to set up virtualized routers with a specific set of security groups, so we tie the whole thing together. We give the correct port access. And there was an issue of concern on one of the connectivities. What would happen if someone gained access to your Lustre router? What would happen if someone gained access to that part of the network? And one of the concerns raised there was, without IP tables, maybe that would become a problem in the future. So it's an area of future research for us. Look at the performance from those virtualized routers. Yes, we have a bit of an impact on the performance, but it actually works okay. We'd take about a third of the performance, but that came down to I/O per box and the fact it's going through an open virtual switch. We actually found if we pushed this really, really hard, the Open Virtual Switch could drop packets. We believe that's being updated in the current release. We're working with Red Hat and others to try and get to the bottom of that one. But already, it's working reasonably well. Again, random access, usual sort of thing, similar pattern. When debugging part of the performance on the virtualized networks, we didn't expect to see asymmetric routing. Precisely, packets coming back from a slightly different direction. And it turns out this is completely unexpected, and whilst it all worked fine, we did hit an issue that we thought, well, hang on, this is going to make debugging an absolute nightmare. It's a bit frowned upon, asymmetric routing. It was working, but not quite right. So we're looking at the moment as to how we can better address that. We don't have a good solution for it right now. Given that it's on layer 3, RP filter is not going to work for us, but there may be some other options that we're looking into. We originally put this together about 2 or 3 weeks ago. A lot more has happened since then. We think we've come to the bottom of some of the security concerns we thought might exist. We don't think they're actually really an issue anymore. They've been patched. We have got people using this heavily in testing, and a couple now in production, in live production. And they're finding actually that it works very well for them. It's providing them proper tenant segregated access to a POSIX file system, which was the objective. We were able to do this without any bespoke software. We can do this with out-of-the-box tools from both OpenStack and from Lustre. The routers themselves, little memory, little CPUs, the actual outlay to make it work, very, very low cost. So we've got a number of future steps. We've got more customers coming on board saying they want this, they want to try this, they want to give it a good kick of the tires. We've got a few more systems in testing that we can hand over, and we're looking to scale this out over the next year, 18 months. Brings me towards the end. Lessons learned before I say thank you to everybody. Moving to a hybrid environment is not without cost. It takes time to migrate from HPC traditional environment towards a distributed compute environment. There's an uplift. As people migrate their code, they migrate their way of thinking, they migrate the tools and so on. And really what we're trying to do is lower the barrier for entry. How do we help people get started? If we can provide people a POSIX compliant file system with performance, we remove that massive barrier to entry. When you move to something new, support is essential, both for our customers, but also for us. This was new to us. This is a new step out of the bag. So we really want to say a huge thank you to DDN, Sebastian in particular, who provided a lot of technical support on this, but also the rest of the team behind it. I'd also like to say thank you to James Beale and the rest of the informatics support group who actually made this happen, take place, and work. It was a rapid summer project which worked far better than we originally expected. It's one of those POCs you think, well, it might have legs, it might not. It's actually worked. So, again, huge thanks to the team involved. We'd also like to say thank you to Intel, who provided a lot of support on some of our original debugging. So, thank you very much.